Hello, everybody. It's 6 o'clock, and welcome to the fourth lecture in the series that we've been exploring called In Situ, the Modern Concrete Skyscraper. And tonight we have Matthys Levy, a structural engineer who back in the 1960s, when the CBS building was being designed and constructed, worked on the project directly with his eventual partner, Paul Weidlinger, who was the head of the firm that Eero Saarinen selected to be the engineers of this innovative modern corporate skyscraper. The first skyscraper office building in concrete in New York, amazingly enough, because in this series, and I'm going to show you the buildings that we've looked at so far, in the series that has teetered between New York and Chicago, with a little more emphasis on Chicago, and then looked at Europe as expressed in Milan and the Pirelli Tower that you can see in our banner across the way. We've looked at buildings from conceived in the 1950s and 60s, and what's been clear across the conversations about these buildings that have been examined by Tom Leslie, and we're looking first at the DeWitt Chestnut building on my left-hand side of the banner. In Chicago, a building by SOM that explored concrete for residential building, and another Chicago building in a completely different form, the Marina Tower that was discussed by Jeff Goldberg, the son of the architect, Bertram Goldberg. The historian, Marco Pagatsnik, looked at the Pirelli Tower in the context of Milanese construction in the post-World War II era. And tonight, to look at CBS as an example of the expansion of the corporate corridors of New York, especially on Park Avenue, and then westward and north on Sixth Avenue is our topic. But we're not really talking about the architecture tonight, because our focus throughout this series has been on the material of concrete and how it represents a kind of hidden history of the skyscraper, which has been told as a story principally of steel. Think of the Seagram building and the kind of the expression of structure, the symbolic expression of structure. But even Mies van der Rohe practiced in concrete as well. So we're exploring this perspective throughout the lecture series. And I want to mention before I forget that we've added an additional focus to the series, and that is to go to the global south and to look at the really spectacular modernism of Harry Seidler, focusing in particular on Australia Square, the first modern skyscraper in the Australian city of Sydney, and Vladimir Belagolovsky, who is a curator and author who has explored many dimensions of Seidler's work, will be speaking on September 5th about that. And we hope to extend the series even farther. This series is developed in conjunction with an exhibition that we'll be doing in the later fall that is on concrete and the skyscraper, a story of concrete that is being guest curated by Tom Leslie, with the collaboration by the structural engineer Bill Baker of SOM. And I'm going to introduce Tom now, invite him to come onto the screen, and Tom is going to do the introduction for tonight's lecture by Matthys Levy on the CBS headquarters.
All right. Well, thank you, Carol. It's a pleasure, as always, to join all of you. And tonight is one that I've been looking forward to for quite a while. As we've looked at CBS, it's become really clear that this is a building that is both kind of unique in its architect's line of work, but also a really important and unique moment in the history of concrete as a structural material for high rises. And we're very lucky to have Matthys Levy tonight speak to us a founder of WAI Consulting Engineers, which in 2015 became a part of Thornton Tomasetti. He served as structural design engineer for hundreds of buildings and bridge projects. In addition to working on CBS, he has worked on the Rose Center for Earth and Space, the Javits Convention Center, and the Marriott Marquis Hotel, all in New York City, the Georgia Dome in Atlanta, La Plata Stadium in Argentina, and the World War II Museum in New Orleans. Levy's the author of several classic books on structural engineering. He'll be a familiar name to anyone who took an architectural structures course in college or grad school. Why the Wind Blows, A History of Weather and Global Warming, and he was co-author with Mario Salvadori on Why Buildings Fall Down, Structural Design and Architecture. Also Earthquakes, Volcanoes, and Tsunamis, and Engineering the City, How Infrastructure Works, with Richard Panchik. He's also a novelist. His first novel, a thriller, Building Eden, was published in 2018. And his second, The Dystopian Heat, A Tale of Love and Fear in a Climate-Changed World, was published in 2022. And this summer seems more like forecast than fiction. So Matthys, I'm delighted to have you here and looking forward to your talk. And I'll join back in afterwards to lead a bit of a discussion.
First of all, thank you very much for inviting me to give this little talk. I was very fortunate to live at a certain time and in a certain place, because it gave me the opportunity to meet and work with some of the major architects of the 20th century, mid-20th century. Obviously, I worked with Royer, I worked with Gropius, I worked with Sturt, and indirectly I worked with Saarinen, although I never actually met him because unfortunately he died before I had a chance to meet him. The CBS building is the iconic concrete structure in New York. It was really the first major concrete building in New York, concrete high-rise building in New York. But concrete itself has an earlier history. It started really with Joseph Lambert, who built himself a rowboat. Now, this is not his rowboat, but this happened almost a century later when Pierluigi Nervi built a concrete sailing vessel built with ferrocement. The original rowboat that Lambert built was just concrete and steel rods. Now, reinforced concrete was finally patented in 1892 by François Hennebique. He patented it, and he also built his own house using reinforced concrete in 1902. And it's a building that still stands today as a museum. In 1903, the first US skyscraper was built of reinforced concrete. That was in Cincinnati. It's a 16-story building. It still stands there. The standard for skyscrapers in New York, though, was a little different. Almost all of them were built of steel. The first one was this, which is the World Building built in 1890, 310 feet high. And then the next one was one that I'm very familiar with. It's the Singer Building. It was built in 1905 and was 612 feet high. And the reason I know this building quite well is because my uncle in the 1940s and 50s had his office in that building. And when I was a teenager, I actually worked for him during the summers as an office boy. So I knew the building very well. The next the next buildings that were of interest were the Woolworth Building, again a steel building, and the iconic Empire State Building, which served as the image for a skyscraper for many, many years. Now, the Singer Building itself was torn down in 1967 to make place for One Liberty Place in 1974. Now, One Liberty Place happened to be another building that I was involved with. It's a steel building, but it's a unique steel building because it serves, its facade is both a structural facade and an architectural facade. The girders you see here on the facade serve a structural purpose. They are part of the support of the building. And the one thing that's unique about those is that the webs in the building are not fireproofed. They are simply naked steel painted. The flanges were, of course, fireproof because a fire inside the building would tend to flame outward, and that was required. Now, how we got involved in the, I'm sorry, how we got involved in One Liberty Place was because we had been working with Gordon Bunshaft on a building in Brussels. This is the building in Brussels. It's the Banque Lambert, and the reason we worked on this one is because Paul Weidlinger, who became my partner, and Gordon Bunshaft were not only friends, but they were the collaborators on many, many buildings. This is again a unique structural elevation that you see on the outside face, made up of these concrete crosses that are supported in the mid-height by steel hinges. And they are actually stainless steel hinges that I was fortunate to be involved in. It was a kind of a wonderful job to see, and I saw it in Brussels, not only when it was being built, but many times later. It's a beautiful building and still is, maintains the quality that was originally built into it. In the time that Saarinen decided to build, or he was awarded the contract for the CBS building, the reason we were involved, or we became involved in that building, was because, again, the relationship between Gordon Bunshaft and Paul Weidlinger was such that Bunshaft recommended us to Saarinen, and we then were not only proposed, but we actually signed a contract for the building, for the structure of the building. Why was it a reinforced concrete? That's a good question, because it could have been a steel structure, but both Saarinen and Paul Weidlinger really wanted to have a concrete building, especially Weidlinger, because his experience, life experience until that point, was primarily in concrete structures, both in the time he spent in Europe and the time he spent in Washington, D.C., where he was designing concrete buildings, low rise, of course, but nevertheless concrete. It also made sense to use concrete for this building, and I'll go into that a little bit more. It's a 38-story building. It has a number of unique characteristics. The facade is one which I'll discuss in some detail. It occupies about 60% of the site on which it sits, and it makes full use of the floor area ratio. In other words, they used every inch of floor area that was allowed by code. At this time, Saarinen actually moved from his original office in Ann Arbor, Michigan, and established an office in Hamden, Connecticut, with Kevin Roach. Now, there were a lot of contemporaneous concrete skyscrapers that were built around the world. One of them was the Pirelli building, which I think you've heard of before. And then there was a lecture on the Pirelli building some months ago. The one that I'm mostly familiar with is this 48-story, 620-foot high Tour de la Bourse in Montreal. In 1964, it was built in 1964, and it was for a brief time the tallest concrete building in the world until 1968. A 70-story building on the Lake Point Tower in Chicago was built. at 645 feet tall, just a little bit higher. The CBS building had to deal with an unusual situation, which was that there was a subway that crossed the site diagonally in order to be able to carry the loads down to the foundations. Steel girders were placed above this tube and encased in concrete. You see the image on the left looks like it's going from left to down right, but the image is correct on the right-hand side where it goes from upper left to lower right. I had joined Paul Weidlinger's office in 1957, and by 1961, I was actually a partner in the firm. When the issue of this particular building came up, I ended up being the designer, especially for the floor systems. This is one of the reasons that concrete became really a good choice for the building. What I decided to do, and what was eventually done, was to design a floor system that was kind of universal all around the building. And it consisted of two parts. And you see it in the upper left of the screen. On the corners, there was kind of a waffle, a two-way slab. And on the flat sides, there were joists going from outside wall to the core walls. Now, this whole slab, the whole construction, was 17 inches thick, and that was the only structure horizontally. No interference, there were no steel beams, nothing else to interfere with passageway of ducts and lights and things so on. So that was a very efficient system that was used. And one of the other aspects of this was that the concrete that was used for the floors was a lighter weight concrete, about 25% lighter than normal weight. Above the slab, there was a 3-inch layer of cement, which enclosed electric and communications wiring. At this time, there was a transition. Well, first of all, let me talk a little about the facade of the building. The facade, as you see it on the outside, consists of granite slabs, black granite slabs, which were chosen by Saarinen, both for the color and for the texture. In order to create the texture that he wanted, the stones, the original stones, were flame tippled and then high pressure honed to bring out the black color. The result was a very, very strong and dynamic structure. Now, what happened, unfortunately, in 1961, September 1st, Saarinen died. He was only 51 years old. And Kevin Roach immediately took over the construction responsibility, design construction responsibility from Saarinen. He formed a new firm, Roach Dinkaloo, with John Dinkaloo in the office in Hamden, Connecticut. Also concurrently, a contractor was named George Fuller. Now, some of the design issues that were present in the building and which you are aware or may not be aware of, the concrete walls in the core. There were concrete walls in the core that separated the floor area of the floor that was used floor from the elevators themselves. These concrete walls were anywhere from 12 inches thick at the top of the building to 8 inches thick at the bottom of the building. They are used to resist wind loads and lateral and as well as gravity loads. Now, the outside wall was also part of the system, lateral force system, because it is quite gutsy, so it could do a job. Now, the floor area, the floor itself of the building was designed based on a 5-foot module. So 5-foot module was used throughout. It's a very convenient module for creating offices. You could have a 10-foot office a 15-foot office, or in the corners somewhere, you'll see also a 20-foot office. The columns themselves on the outside face, what you see is a column that is a 10-foot on center. So the window in between is about 5 foot wide, or including all the framing, but the actual glass is a little bit smaller than that. The 35-foot span from the outside wall to the core is actually also a very convenient number for not only the office layouts themselves, but also in terms of the distance from the outside wall with glass and the core, which is black. So you don't want to have an office too far toward the core because it has no natural light at all. So 35 and 40 feet is what you'll find many office buildings as a dimension from core to outside wall. When it was finally built in 1965, completed in 1965, critics talked about the building and they said, well, someone said, it's a classic building, it's dignified, it's aloof, it's forbidding, and the public called it funereal. But nevertheless, the building is so elegant that it was designed as a landmark in 1997. Now, sometimes when, as engineers, we try to do a good job, and sometimes things go wrong. For instance, this is the HUD building in Washington, D.C. Now, nothing went wrong structurally, but when we were working on design, the floor system was initially designed as a poured concrete floor. We suggested that be changed to precast. Therefore, we had precast joists similar to the ones in the CBS building, only precast, not poured in place. That change from the poured in place to the precast system saved millions of dollars. Unfortunately, our fee was based on a percentage of construction cost, so our good idea ended up costing us money. When Kevin Roach took over the construction responsibility for the building, he very soon also obtained other clients. For instance, in the 1964-65 World's Fair in New York, IBM hired him to design the pavilion, the IBM pavilion. And he and an interior designer came up with this egg and also a steel trees below the egg that formed a canopy, and was used to an announcer who dropped down from the steel canopy and announced the next show. The show itself was on a movable platform that entered the egg itself. Another building that he designed, and unfortunately it was not built, was Saitama Arena in Japan. Now, Roach also designed other buildings as well. One of the most famous is the Ford Foundation headquarters that Paul Goldberger called quirky, but it was a very, very elegant building, and it's still standing today. And a clear idea for a different kind of structure that mixes the requirements of and ends up really satisfying the requirements of the foundation. We were involved in other concrete buildings. For instance, the Southern Bell Tower in Atlanta. It's a concrete tower, 47 stories high, 677 feet for Southern Bell. The reason you see at the bottom that something goes on is that the building could not continue down to the bottom with the same dimension, because on one side there was a subway for MARTA station, and on the other side there was a Fox Theater, the Fox Theater, which was a landmark building. So you couldn't impinge on either of those. So the building is actually cinched in at the bottom with a girdle, and the girdle is tied across with these pre-stressing rods, which are expressed on the face of the building. That same idea was used in other buildings as well later on. One Main Place in Dallas is another interesting structural building because it was done roughly at the same period. It's a 33-story tower, 445 feet high. It occupies about half the site. SOM was the engineer for the architect for the building. We were consultants only on the facade. What Gordon Bunchap, who was the principal involved, architectural principal, wanted to have a facade in concrete, but he wanted to have it a little bit livelier. So instead of having just gray concrete, a granite aggregate was used in the structure of the facade, and then it was brushed in order to liven up the visual impact. So you can see it. You can see some of the granite peeking through. Now, as a result of COVID, what happened to this building and many other buildings is suddenly there was a surfeit of office space. And we know that happened in New York, and it happened in Dallas as well. So what happened here in Dallas is that the building was changed, at least the first 10 stories of the building were changed to a hotel. It's now a Westin hotel. So only the upper portion of the building is actually an office building. Now you have many examples in New York of office buildings that have been converted to apartments, and some even to hotel occupancy. But that's a trend that's going on, because there are, as a result of COVID, what happened is that people got used to working at home, and they didn't want to go back to the office. So that idea of using an office for a meeting and for conferences sort of modified it. You don't need as much office space because only part of your staff is going to be in the office at any one time. So that's a continuing problem, and you'll see many, many more buildings being converted. There's another aspect to this, and that is that there are mixed buildings where you have both concrete and steel being used. This is the Marriott Marquis Hotel in New York, and it consists of two parts. One, the elevator core, which you see it's a round elevator core going up the whole height of the building, and a steel frame on the outside for the wings of the building where the actual rooms are. That mixture was also followed on another structure in Cleveland, the Cleveland Trust Company. We happen to have designed that building as well. It was originally envisioned as a building with a concrete core and two steel framed wings for offices. What happened there as well is that, well, first of all, only one of the wings was initially built. And then the same thing that happened in Dallas and in New York, suddenly you didn't need the office building anymore. So it was converted to apartments, totally apartments. And the concrete core, which you can see here on the left, which took all the lateral forces. It was really the strength of the building itself, was all of concrete. We originally had proposed that this building, at least the core, be slip formed, because I had been in Tunisia when this slip formed control tower was built. So I kind of liked the idea of slip forming, and unfortunately they decided in Cleveland that it was not necessary, so they just jump formed the way concrete was conventionally done. And finally, I want to, I only included this because in the front, lower front, you see Marcel Breuer, the architect for the building. Now we go to what is happening today, which are these sliver buildings. And there's sliver buildings left and right in New York City. It's like when you look at it, it reminds you of stalagmites growing out of the core of the city itself. It's an unfortunate turn of events. They are, as you see here, when compared to normal, or what I call normal buildings, in terms of size and their aspect ratio, their narrow elements climbing into the sky, just like stalagmites. And you see the comparison here to classical buildings. The recent Steinway Tower, which you see here overlooking Central Park, is one that climbs 1,428 feet high, 82 stories high. It has a height to width ratio of 24:1. It means it can sway at the top as much as 3 feet. There's something very fragile and unsubstantial about it. Frankly, I wouldn't care to live on the top of such a fragile flagpole. And it's a far, far difference from the solidity that CBS gave us 60 years ago. Thank you.
Thank you, Matthys. A wonderful talk, not only about CBS, but also I think its sort of legacy and how a lot of the structural, but also architectural issues that CBS dealt with so forcefully and so successfully continue today. And I particularly like the comparison with the so-called super skinnies at the end, where maybe we're so confident in our engineering today that we can appreciate buildings that appear a little fragile. But the contrast with CBS, which, as your title slide mentioned, was actually called Black Rock, talking very much about the solidity of the building is a really interesting one. Matthys, I wanted to start just by picking up on one of the points that you made, that CBS was one of New York's first concrete skyscrapers, depending on how you define concrete and how you define skyscraper. But it was a break, certainly. We think of commercial skyscrapers of that era, certainly of the 1950s, as being mostly in steel. And I wonder if you could talk a little bit, a lot of the examples you showed toward the end of the talk showed how versatile concrete is, how it could adopt a number of forms, how it could do structural things that would be very difficult in steel. And I wonder if you could talk a little more about what concrete allowed you as an engineer, but also Saarinen and later Roche as architects to do that steel would not. And I'm thinking particularly of the detail of those piers that incorporated a great deal of the mechanical system as well.
Right. Well, one of the things that was very, very unique about the piers themselves is using concrete. Concrete is a plastic material. It'll take any form you want. And the advantage here was the outer face was a V shape, but the interface was not defined. It was just flat inside the building. But the structure of the concrete piers clearly did not have to be one dimension, because it needs one dimension at the top, and it gets fatter and fatter as you go down to the bottom. So the shrinking of that dimension allowed the space in the middle of that triangle to get larger and larger as you go up, and smaller as you go down. It allowed as you said, it allowed the passage of ducts and other services to go up and down the building. One thing I didn't mention, by the way, which was very unique about the piers, is the mechanical floors were on the second floor and the top floor of the building. Second floor because you couldn't have a real basement as such because of the presence of the subway tunnel. So most of the mechanicals serving the lower half of the building are on the second floor. How do you get mechanical equipment in and out of that space? You only have a 5-foot wide window everywhere. So what was done is very unique. One of the corner piers is actually removable. So it could be removed and you suddenly have a 25-foot space that you can move in equipment in and out of the building, and then bring this facade piece back in. Now, if you ask me which corner it was, I don't remember.
I have, since you mentioned that in one of our preliminary discussions, I have looked everywhere for a photograph showing that. I would love to see.
Well, there is one.
Is there?
Actually, I have one. I mean, there's one that Carol sent me.
One
of the articles.
I'll have to run back and see it. That brings up a good question, though, which is that the corner columns in any framed building are of course carrying just half the load of a normal facade column. And in Saarinen here was clearly, the building is more about structure in some ways than it is actually expressing the structure. That corner column is certainly one of them, but the fact that the corner columns are the same size as the regular piers is another one. And I wonder if you could talk a little bit about the relationship between the aesthetics of the building and the structure. Clearly, it's a very, very clever solution to integrate the mechanical system, but it also emphasizes the kind of pure geometry of the facade when, in fact, the concrete, of course, is carrying less and less load as it goes up. And I wonder if that was ever a discussion, or if the kind of vision of that facade and those piers was so strong that was just always there in the project from the beginning. Oh
yes, well, there was never a thought of changing the dimension as you go up, because the architectural vision of the columns was really the major element in the building. And what happens is when you go to the corner, of course, not only is it carrying less load, but it's twice as big. The corner column really is twice as big as a typical column, and yet it carries much less load. But that's because the whole geometry was so strong and so well defined that you couldn't violate it in any way by introducing another element, a different kind of an element. So the rigid geometry was carried through everywhere.
Yeah. One building that CBS was compared to sort of famously was the Brunswick building in Chicago, one that came up in the lecture that Bill Baker gave. And there's an interesting contrast between the two, because one of the issues with a tube structure, and CBS is, I would say, it's sort of a semi-tube structure, right? It relies on the density of columns around the perimeter to provide stiffness. One of the problems, of course, is that you want those columns to come all the way to the foundations. And when SOM did the Brunswick, they were worried about the effect that would have on the entrances, that you'd be forced to come in through relatively narrow spaces. So they lifted the entire building up, right? It's a tube that's actually kind of up in the air on kind of piers. And Saarinen and Roche clearly had the kind of, fortitude or courage to say, no, the tube comes straight down and we'll figure out a way to get 5-foot entrances to feel appropriate to the building. It's one of the major differences between the two. And it's something that, when the two got compared in the 1960s, CBS won in the architectural press all the time because it's such a clear vision. But I wonder if you could talk about the way that structure or that building comes down to the ground, how important it is to have the continuity between the concrete structure above ground and the foundations below, and whether you recall any discussion about altering the column spacing or trying to carve out sort of larger entrances in it to match the generosity of the plaza that surrounds it.
There was never any discussion about that, and I know the Brunswick building quite well because we were in touch with Faz Khan. We were kind of close as engineers and comparing buildings we worked on, and I never frankly cared for the base of the building of the Brunswick building. I thought it really interrupted the whole elevation in a very brutal way. And it's not clear how it carries the load. It's just kind of brutalist, but not. It doesn't have a style. It doesn't have style really. And one thing you can say about CBS, it had style because it really was designed in such a way and built in such a way that it was totally honest how it worked. And you could see, anyone could see exactly how it worked.
Yeah, even right into the furniture, which I know Saarinen's office had a big hand in. There was this sort of sense that the style goes from the overall building just down into the very details, and even the sort of carpets and desks that were chosen.
Florence Knoll, I think, was very heavily involved in that.
Yeah. And yes, even as a Chicagoan, I have to admit that CBS is a much more elegant. It feels like a much better kind of tailored suit in a lot of ways. Even if the Brunswick has interesting structural kind of gymnastics that are interesting to look at. I am curious too, just as you were describing the genesis of the project, and particularly the problem of the subway underneath, which is sort of brilliantly hidden, right? There's no evidence that all of the kind of transfers and gymnastics underground, or none of that daylights at all. But I am curious, in a concrete building, that the solution to bridging the subway were these giant steel girders. And I wonder if you could talk a little bit, if you recall, about what the rationale was for switching materials when it came to sort of bridging the building over the subway tunnel.
Well, basically, if you think about it, you would have ended up with so much steel in the concrete that it's equivalent to having a steel girder in there, because the flanges in the steel girders, you would have had the equivalent amount of reinforcing steel in the concrete, and it was from a really practical point of view. You could get them manufactured very quickly and put in place very quickly, and they had to be carried on piers as well, because you had to go on. You had to envelop the subway tunnel to get it down to the bedrock.
Yeah, that makes perfect sense. If it's going to be a steel structure anyway, right? You might as well go for the actual material instead of reinforced concrete. And I guess one sort of following on from that a little bit, you described briefly the thinness of the floor plates, which of course is one reason that we use concrete in residential high rises all the time. Residential high rises don't typically have as much ductwork as commercial buildings, and so we don't really get to use that space that you get with steel for mechanical systems like we would have to for commercial. I'm curious about the integration of the mechanical system then. Was it just that the ducts could basically go anywhere? And maybe if you could talk a little bit about why concrete was such an unusual choice for commercial buildings, and that integration which happens so well in the columns, but seems to me that you're not getting quite as much of your floor to floor heights money's worth as you would if it had been a residential structure. What, in other words, is the rationale for doing a commercial skyscraper in concrete in the early 1960s?
Well, But first of all, one thing that I didn't mention is that there was a question of cost involved. It turned out that the design was quite economical and compared very well with the steel structure, an ultimate steel structure, and some of the just physical advantages of having a clean floor plate, which meant you could have ducts and lights placed almost anywhere you want, and you were not restricted by having girders in the way which you would have had in a steel structure. So that was one advantage. The other, I think, is the fact that the outside columns carrying some of the air conditioning ducts, really that's what they are. Air and hot air and cold air was carried up in those columns. If you didn't have that, you would have had everything carried in the core, and you would have to go across the floors to feed the rest of the building. And since a lot of the need for air conditioning or heating of the outside wall or cooling in outside air is done because you need a lot of it on the perimeter, not so much on the interior. So it kind of makes sense to have vertical ducts on the exterior building.
Almost like the building is a traditional central core mechanical plan just turned inside out, right? That it's all fed from outside in instead of inside out. Which I guess also makes looking at the floor plan, the core of CBS seems so compact. And I guess one of the reasons is that the ductwork is all like migrated to the perimeter. It was not the only structure like that. I can think of a couple in the 60s that incorporated ductwork or at least pipework within the perimeter structure, but it seems to be done so elegantly. When you look at the one cladding detail of the little duct surrounded by the concrete column, you realize that there's a really, really good conversation going on there between architect, structural engineer, and mechanical engineer.
Yes.
About how all of that is going to get sort of tied together. And I guess one other question I have about that, the perimeter detail, going back to Brunswick, one of the things in researching that project that surprised me was that we think of it in Chicago as like one of the most, expressive concrete buildings. You see the actual structure that's holding it up and all of this, but it was originally intended to be clad entirely in travertine. So instead of this, sort of strong Chicago concrete building, it would have been this very, very bright white structure. And I'm fascinated by the decision in Saarinen's office to clad the building in black granite to go with the very, very dark windows. And one of the things I think that does is it makes it feel like a solid block, right? You don't really get the sense that there are windows in it until you're right up close. But I also wonder whether you recall any discussion or whether you have any thoughts on the fact that, here's a concrete building where you don't actually see the concrete, you see the form of the concrete, but it's clad in this admittedly very, very beautiful, deep black granite, but very intentionally, right? Saarinen, who elsewhere, in TWA seemed very happy to let you see the concrete shell. Here for his one skyscraper felt that the structure had to be clad in stonework and dark stonework at that. And I'm wondering, as a structural engineer, does that, what thoughts do you have on that?
First of all, one thing that I didn't mention is behind the stone there's insulation. So essentially, the building is insulated from the outside, and then you have stone on the outside. If you have a concrete building with an exposed facade, there's no insulation. So the building, the outer face, expands and contracts with temperature. Here, it's steady, completely steady. That's an advantage.
Sure.
the fact that in the concrete building, there are pure for instance, in Atlanta, the building in Atlanta, it happens that the temperature variations there are not as extreme as they are in New York. So in Atlanta, although the concrete facade expands and contracts, it will not create a problem. But in a building where you have extremes of temperature, where you can go down to temperatures below zero and the temperatures approaching 100 degrees, you have a wide range of expansion and contraction, which can cause damage to the building, actually, can cause fractures. So I think that's an advantage of doing it this way.
Hmm. And
location is very important,
Yeah, in Miami or Atlanta, you would be dealing with all sorts of maybe other issues.
There are other issues, definitely.
Yeah.
Tom, can I introduce a question as a disembodied voice?
Sure.
Because when I hear Matthys or you talk about a tall, dark, elegant post-war skyscraper, you can't help but think of the Seagram building, right? And I would like Matthys to comment on how self-conscious was the comparison in the design process and every other process of creating CBS to the already iconic Seagram building by Mies van der Rohe.
Yeah, well, there are differences between, well, first, if you look at the Seagram building and compare it to CBS, again, CBS is a building that goes down to the ground. Exactly where it starts, it comes down to the ground. However, Seagram doesn't do that. It's also picked up. It's picked up, I think, at the second floor, so that the columns or the facade, structural facade, does not go down to the ground. That's a major difference between the two. Again, it's a question, but they're both elegant in their own way, just like the what I showed, One Main Place, which is I think a very elegant building, also, even though it is different. But it also has the advantage that the structure continues down to the ground. The columns continue down to the ground. They're not interrupted in any way, and I think that gives it a certain style. Elegance.
Before we leave Seagram, I do have a question about the 5-foot module and the window wall relationship, therefore being equal. That, of course, is utterly different than not only the Seagram building, but the glass boxes like Lever House and their replication across Park Avenue, and also at the same time on, across the street on Sixth Avenue. So was do you know with the architects, or what was the discussion in your office about the virtues of as much wall as window as an interior environment, or even as an insulating or any other advantage for the functionality of the building?
You're talking about the 5-foot 5-foot module being active. Yeah, I mean the 5-foot module.
There's as much wall as there is window, right? They're equal.
No, they're not. No, you have a 5-foot window and 10-foot wall, really. Okay. So there's more wall than window.
Right, which is opposite of the glass box, the stretched membrane of Lever House. Mm-hmm. And so, even with that, was there much discussion, whether even for CBS or anything else, about the virtue of having an exterior wall as part of the experience of the interior work environment?
I think there was a discussion about the advantages of having a more exterior wall for offices. If you have an office that has a lot of glass, an all glass office has on the outside, that has some problems in terms of layout. you can't have your desk right on the outside wall. You don't want to have the light coming in, and so you got some interior issues that come up, and I think the offices work extremely well because there's in a 15-foot office you've got a 5-foot piece of glass and 10-foot behind it or next to it, and that 10 feet serves extremely well for placement of desks and placement of furniture. If you change that and had all glass, or even reverse it and have 10 foot of glass and 5 foot of wall, you've got problems in interior layouts.
But yet the minority of buildings that are created after CBS, and one of the questions was there a lasting influence of CBS on other tall buildings, whether in New York or other places, or was it an experiment without many progeny?
If you follow the buildings that were built subsequently to CBS, a lot of all glass buildings, and obviously that's totally different because you had, they ignored in that way the problem of interior layouts. They simply said it's an all glass building. You've got to deal with the facade totally differently, and your offices are going to be totally different. One of the reasons that was true is that the office began to disappear. I mean, the individual offices began to disappear. So the all glass facade has the advantage that you have an open layout and the light streams in quite deep into the space, the open space. So that really made it quite different. If you look at the layouts, which I've seen, interior layouts of firms that used open office layouts with a glass facade, it works extremely well, total glass facade. But that wasn't what CBS wanted. CBS, as you saw in the layout, they wanted a lot of small offices. And so they worked very well for them to have it this way.
Someone wanted to know if there were any television studios within the building or radio studios.
There were. I think they were on the interior though. I don't know that much about the interior layout, but I know that there were studios. They eventually moved the studios out.
Be a relatively small, that the 35-foot core to skin is small for a broadcast studio, I'm sure. Yeah.
Tom, any last thoughts or questions?
No, Matthys, this has been a real joy to speak with you and to talk to you beforehand as well. And again, looking at CBS, it's a building that I knew in passing, but to get to know it this much better and realize its kind of place in the history of concrete, but also in the history of skyscraper design has been great. So thank you. A real honor to speak with you, and as one of those architecture grad students who has had your books on his desk and still has them very thumb worn and well loved. It's been great to speak with you about CBS, but also about your career.
Thank you very much.
Well, I certainly second that in all of the dimensions, both with the specificity for the series that we're pursuing, but also the way you put it in context for us within your own experience and the architectural decades that come after. I will mention that we're thinking of doing a second program on CBS later in the fall, because there are lots of fans of the building, given the strong response to this webinar, but also scholars of Saarinen and authors about Saarinen. And then we think of our New York colleagues, Jane Merkel and Donald Albrecht, and also Alexandra Lang. And I know that Deborah Burke gave a talk in Indiana of Cummins about CBS built about Saarinen, and about the CBS building being her favorite skyscraper, her favorite Saarinen building. So I think we have a lot of fans who would enjoy focusing especially on the architectural design and the context in Saarinen's career. So we will explore that later in the semester, as it were. But we want this to be an evolving series. We're excited too to be going to Australia for our next talk, and we're open to additional ideas for the people who would like to propose to us. So Matthys, thank you for bringing us back to New York tonight and teaching us about the first modern concrete office building in New York City. Who knew?
Thank you.
Okay, thanks.
If you go to Australia for Seidler, right? And Seidler, of course, worked for Breuer at some time.
Yes, absolutely. And Vladimir Begolovsky will inform us of all of that background and context too. So we're going to come back.
I met him in Australia.
Great, a great modernist.
Yes. Thank you again.
See you next time. Bye, everybody.
Bye.